Ever wonder what happens when you smash, like really smash, particles together?
Yeah.
Well, buckle up because today we're going deep, and I mean deep, into the world of particle physics.
Deep dive time.
Exactly.
Yeah.
We're talking about the tiniest building blocks of the universe.
The quantum realm.
You got it.
Yeah.
We're diving into some seriously cutting-edge research on something called parton showers. You with me so far?
Parton showers, got it. It's like trying to see what happens right after the Big Bang.
Whoa, okay, so we're talking big explosions here.
Kind of, but on a much, much smaller scale.
So what are we exploding, exactly?
Particles. Imagine like two protons smashing head-on at almost the speed of light.
Okay, I'm picturing it. What happens next?
Well, you get this burst of energy, right? And from that energy, a ton of new particles pop into existence, like fireworks.
Subatomic fireworks, I like it. But these fireworks, they're not random, right?
Not at all. That's where the parton showers come in. These simulations help us see how the particles, interact and decay based on the fundamental forces of nature.
Forces like, wasn't it quantum chromodynamics?
QCD, yeah, and
Yeah.
quantum electrodynamics, or QED.
Right, those two. So it's about predicting that chain reaction, right?
Yeah.
After the initial particle collision.
Precisely. And the more accurate these simulations are, the better we can understand what's really going on at the most fundamental level.
So we're talking about tweaking the very tools we use to study the universe.
Exactly.
That's wild. But why is it so hard to make these simulations super accurate? What's the deal with QCD and QED?
Well, they often work on very different scales. It's a bit like, trying to model how a feather moves in a hurricane.
You've got the huge forces of the storm,
Yeah.
and then you've got this tiny feather just trying to exist.
Exactly. It's hard to get all those different forces playing together nicely in the simulation.
So you know how we were talking about those two forces, QCD and QED?
Right.
Well, it turns out they don't always get along. Kind of like trying to bake a cake with two chefs
Yeah.
who have very different ideas.
Huh. I like that analogy.
This research paper we're looking at uses a specific interaction. It's E plus E minus 2.
E plus EQ?
Yeah, that one. To show how these forces can clash.
That's a great example.
So let's unpack this E plus E cucuth interaction. What kind of particle party are we talking about here?
Well, you start with an electron, that's the E, and its antimatter partner in crime, the positron, or E plus. When they collide, poof, pure energy.
That's always so weird to me, how something and its anti-thing can just become energy.
It's wild, right? But that energy has to go somewhere, and in this case, it creates two quarks and two antiquarks, hence the Q-kook.
Okay, so we're going from these tiny particles, electrons and positrons, to quarks, which are like the building blocks of protons and neutrons, right?
That's it.
It's like zooming in on the very essence of, well, everything.
And what's cool about this E plus E kook interaction is that it can happen in a couple of different ways. Each one governed by either the strong force, that's QCD, or the electromagnetic force, QED.
Hold on, so it's like having two different recipes for the same dish.
Exactly. One recipe might call for like a slow simmer, while the other needs a quick sear.
So we've got these two competing chefs, QCD and QED, both trying to control the outcome of the dish. How does that impact the simulation?
Well, because, QCD and QED have different strengths and different rules. Those different paths can lead to slightly different outcomes.
So it's like what? Trying to predict where the splatters from a water balloon will go?
Yeah.
The forces involved.
But the exact result is hard to pin down.
Exactly. And these little differences, these like tiny variations, that's what the researchers are trying to nail down with their new simulation.
Exactly. They want to make the simulations more sensitive to those different pathways.
Okay, so how do they do that?
Well, they use this cool tool called color flow.
Color flow. I've always loved that term. It sounds way too simple for something happening at the subatomic level.
Right.
So how does it work? How do physicists actually use color flow to understand these like crazy particle interactions?
So imagine, each quark is carrying a color charge.
Not actual colors.
No, not real colors. It's just a way for us to visualize it. Think red, green, blue.
Got it. Like those little packets of flavoring you add to water.
Exactly. And gluons, those are the particles that carry the strong force. They've got these color charges too. So when quarks and gluons interact, it's like mixing those colors together.
So each interaction leaves behind a unique color trail.
Yeah, like a fingerprint. And by following those color flows, physicists can differentiate between all the different ways the particles might interact, even if they produce the same final particles.
Wow. So it's like Not just knowing who baked the cake, but the exact recipe they used.
A perfect analogy.
But how does this help the researchers improve the actual simulation?
Okay, so traditional simulations often just kind of average over all the possible color flows, right? But this research takes a more detailed approach, using something called fixed color QCD evolution.
Fixed color QCD evolution.
Yeah, it's a mouthful. Basically, they run the simulation a bunch of times, but each time they assign specific color configurations to the quarks and gluons.
So instead of blindly mixing all the ingredients together, they're trying each recipe one by one.
Yeah, exactly. By fixing the colors, they can capture a wider range of possibilities, making the simulation much more sensitive to those interference effects between QCD and QED.
Okay, that makes sense. But they didn't stop there, right?
No, they didn't. They also incorporated something called QED evolution.
QED evolution. More chefs in the kitchen.
Haha, kind of. They wanted to see how photons, the carriers of the electromagnetic force, might be, subtly influencing that cascade of particles.
It's like adding a pinch of salt without telling the other chefs.
Exactly. And finally, they threw in what's called kinematic matrix element corrections.
Kinematic what now? Okay,
Yeah.
that one sounds a little intimidating, even for a deep dive.
It's simpler than it sounds. These corrections just make sure the simulation follows the fundamental laws of physics, things like conservation of energy and momentum.
So like no cheating with extra ingredients from off screen.
Exactly. It's all about keeping things realistic.
Okay, so they've gone through all this trouble. Color flow, fixed color, QCD evolution, QED evolution, these kinematic corrections, all to make the simulation as real as possible. What did they find?
Well, you'd expect some pretty dramatic differences, right? But that's not what happened.
Wait, seriously. All that and the QCD-QED showdown was a bust.
Kinda, yeah. They actually decided to focus on a slightly different interaction this time, similar to the one we talked about before, but with a twist.
Okay, what did they change?
So remember how we had those 4 quarks, QQ? Well, this time they made 2 of them different types.
Interesting. Did that make a difference?
A big one. See, that little change really messes with the possible color flows, and that changes how QCD and QED can interact.
So it's like they were trying to stir up some trouble on purpose, see if they could force QCD and QED to throw down.
Precisely. It's a really smart way to try and isolate those interference effects.
So what happened? Did those interference effects go wild?
Here's the thing. Even with all the fancy upgrades, all the color flow analysis, the QED evolution, the interference effects, still pretty minor.
So they went through all that and found out QCD and QED are actually pretty chill?
Well, in this specific scenario, yeah, but that doesn't mean all that work was for nothing. Sometimes the most important discoveries are the ones that tell us, hey, maybe we don't have to make things as complicated as we thought.
So good news for physicists who hate complicated math.
Maybe. But it also tells us our current models for QCD might be more solid than we realized, even without factoring in those tiny QED interferences.
So more research is needed, but at least it seems like we can simplify some of those calculations.
Yeah, possibly.
But where do we go from here? What's next?
Well, think about it. We have these incredible new simulation techniques now.
Right.
We can start looking at other particle interactions with way more precision than we ever could before. Imagine zooming in on how different types of quarks interact, or even more exotic particles.
It's like we've got this brand new high-powered microscope.
Exactly. Who knows what we'll find?
That's the best part. It's like we've only just begun to explore this whole universe of tiny particles.
And it's a much bigger universe than we ever imagined.
Way bigger. Well, I think that's about all the time we have for today's deep dive.
Time flies when you're exploring the quantum realm.
It really does. So to all our listeners out there, thanks for coming along on this wild ride with us. And remember, even the smallest particles can hold the biggest secrets. Until next time.